All right, let's get started then. So my name is Fabian Yamaguchi, and I'm going to be talking about ShiftLeft Ocular today, the Google Maps for auditing your code. Let's see, how does this work? There we go. So a few words about myself. I have a background mostly in vulnerability discovery. So I worked as a vulnerability researcher for a company in Germany called Security Labs, GmbH, for a few years. And I was more or less tasked on a regular basis with identifying vulnerabilities in software manually. So that included source code audits, binary code audits, or simply black box tests. And what I found back at the time was that the tooling we have to do these kinds of audits is rather limited. And eventually I was a bit frustrated with the situation. And I decided to go back to university and actually do a PhD on developing tools and techniques that we could use to make the life of vulnerability researchers and security auditors easier in practice, with a focus on automating lots of little tasks based on all sorts of pattern-based approaches. So the question was mainly, since what we do is rather repetitive, can we maybe exploit these patterns to get to the bugs faster? And I did that from 2012 to 2015. Eventually finished that thesis, and during that time I developed an open source code analysis platform called Yearn, and you see the logo in the bottom right. Yearn implemented the idea of taking what's called a code property graph. We'll see what that is in a minute. Putting that into a graph database, and then allowing this code representation to be mined for vulnerabilities. Today, I'm the chief scientist at ShiftLeft Inc. And essentially what we're doing here is we're developing different products, but one of the products, and the product that I want to talk about today, is ShiftLeft Ocular. And if you have played with the open source code analysis platform Yearn, then you can think of it as taking Yearn and building it for real, making it production quality software as opposed to a research prototype. All right. So this is Ocular, and Ocular can be downloaded from our website. So if you go to Ocular free trial on Go ShiftLeft.io, you'll find the possibility of downloading the tool that I'll showcase today. Now, Ocular is a tool that's aimed at highly technical users. So this is a tool that's interesting not so much for CISOs, but more for security analysts, people who really work with the code and are really interested in finding the small flaws in the code that allow for it to be exploited. And of course, developers who are interested in securing the software that they're writing themselves, they might find that just as interesting because it essentially allows to find out how code works. And I guess a lot of developer time goes into understanding how code that other people wrote or that you wrote a few weeks ago actually works. The initial Yearn was implemented for C and C++ using a fuzzy parser. At ShiftLeft, we actually recreated everything from scratch. And today we have code querying across different programming languages. And these languages are Java, C#, and C++. Now, if you download the trial version, you will only get the Java language frontend. Just a second. Oh, there we go. You'll only get the Java language frontend, but if you buy the full version, you get the other two as well. And there are some other languages in the works, but yeah, feel free to ask us if your favorite language or your target language is not supported. What you can do with Ocular, and this is what I'm going to demonstrate today, is essentially two things. You can discover how your program is structured, how it interacts with the outside world, how an attacker can interact with it, where the attack surface really is. And the other is you can look for vulnerabilities based on code patterns. And this in combination is pretty powerful and has allowed us to identify a lot of vulnerabilities in a much shorter time frame than you would require if you did not have that tool. And that, I guess, is what I would like to convince you of today. All right. So when you go online and you type in code property graph into a search engine, you'll find a bunch of different presentations on this. And most of them are rather on a theoretical level. And today I want to keep the theory very short because I mostly want to demo what our product looks like. But what you should keep in the back of your mind whenever I say code property graph is what we've done is we've taken lots of different program representations. So things like a package hierarchy or an abstract syntax tree, control flow graphs, dominator trees, all these kinds of representations that are used inside compilers or just inside IDEs to visualize how your code works and to provide different perspectives on your code. We've taken all of these and we've merged them together into one graph structure so that you can ask questions about all these aspects of code, so query all these aspects, and also you can jump from one representation to the other within a query. Now today, so this is kind of like a symbolic picture of what that looks like. We actually, this graph has multiple layers, and today you'll see what's in the Ocular trial version. And in that trial version, you're essentially dealing with the two lowest layers, which is a layer that gives you access to the different instructions, the syntax of the code, control flow, instruction semantics in terms of data flow. And based on that, you can then calculate data flows, you can calculate call graphs and type hierarchies, and we're going to see that in action today. All right. So to make this hands-on, we've chosen one target that we're going to look into today, and that's a program called OpenRefine. So this is a Java program, and OpenRefine at some point was called Google Refine, and it's a tool that journalists use to refine messy data. So you can imagine a journalist gets a public data that is filled with, for example, the contractors that a government has assigned, and in there, well, sometimes something will be called, sometimes you'll have typos in there, and so OpenRefine is a platform used to clean these things up. And so it's a tool that people install on their computers locally, and it brings all sorts of file formats that it needs to parse in order to import data. So an attacker here might be somebody who goes to a journalist and provides this data, and if there are any flaws in the processing of this data, then this can lead to the situation where the journalist's data is exfiltrated. Right. So what we'll do now is we'll actually jump right into using our tooling, and we'll begin by exploring this code base. So I haven't really said a lot about what's in there, and the reason for that is that we're just going to find this out with Ocular ourselves now. And we'll see two tools. First of all, we'll see Java to CPG. That's a program that takes Java bytecode and converts that Java bytecode into code property graphs. So into our internal intermediate representation that we can then query. We will then see how this code property graph is loaded into Ocular, and we'll then run a bunch of different queries to see how the code can be accessed from the outside world and how it interacts with other components. So you should now see a shell, and what you see here is what you get right after installing the Ocular tooling. And there's that program Java to CPG. And I just said that it's Java to CPG takes in Java bytecode. Now what it takes in is actually a jar, so a Java archive. But Java to CPG in the tradition of Yearn is not too picky about what these Java archives look like. So you don't really need a manifest or anything, or you don't need to put your your class files into any specific order. It's enough if it's essentially a zip file containing class files. And I'm going to demonstrate that now. So I've unpacked this OpenRefine into a directory, OpenRefine 3.1. And OpenRefine actually does not come as an executable jar. So what I'm just going to do is I'm just going to say, find all the class files in there, and then zip them all together and call that OpenRefine jar. All right. And so what you see now is we have a zip file called openrefine.jar, and in there you see a bunch of class files, and this is what we're going to be feeding to Java to CPG now. All right. So yeah, not downloads. There we go. So OpenRefine jar is here in this directory now, and Java to CPG receives that jar. And now we can initially tell it about different namespaces that we're interested in. So given that this code base was once at Google, there's one namespace called com Google Refine, in which the OpenRefine code is, and another called org OpenRefine. And we're only going to take this code. And once we run this, we get a code property graph. There we go. So now we have a code property graph. There are a lot of messages coming in. Let me just quickly check. Okay. So I will answer all your questions in the end. I was just checking whether somebody says I can't hear you. That would have been bad, but you can. Okay, that's good. Okay, let me see. Okay, so we have a code property graph now, and it's 15 megabytes, and we can now load this into Ocular. Okay. So this is the interactive Ocular shell. I'll later also show you that you can use this non-interactively. What I'm going to do now is load that CPG, and the CPG is loaded, and we do a bunch of transformations and enhancements on it. This can actually be done just once, but currently in the default settings, these transformations are done every time. All right, so now the CPG is actually loaded, and the next step is we would like to find out a bit about the different types that exist in this program. So we can say something like CPG type decal name, and we will get a complete list of all of the types that are used in Ocular. Right. And now we can start filtering on these. So for example, we could ask with regular expressions, please give me all the types in Java lang. There we go. Yeah, and that will give you different types inside Java lang. And so now one nice feature of this is we can actually differentiate between types that are used by OpenRefine itself and types that are referenced, like outside types. So we can say, please only give me external types, and actually from there go to the namespaces, right? So the packages essentially, and give us the names of those namespaces. We can also ask for this to be distinct and to be sorted. There we go. All right. So this gives us a view of all of the different namespaces used. There's also a nice browse function that you can use to get all of this into a pager. There we go. So now it's inside a pager. And so those are the different packages that are referenced by OpenRefine. Now, going through these, what we see is there is Java util zip in here, and there's also Java X XML stream in here. And so getting that kind of information is pretty useful because many of these libraries are associated with typical kinds of vulnerability patterns for these libraries. And what we'll see in a bit is that we can actually find vulnerabilities associated with these libraries in particular. All right. Now, the next thing we might ask ourselves is this a web application? Is this something that we can access from the outside? And what we can do there is we can just look for types called something HTTP, just as a wild guess, essentially. And I'm just going to say name. There we go. All right. And what we see here is that there's actually a type being used called HTTP servlet request. And well, people who've audited Java applications, Java web applications, know that these are requests that come in via HTTP. And so any data that comes from there is potentially attacker controlled and needs to be handled with greater care. And knowing this now, we can actually ask for all parameters which have an evaluation type of HTTP servlet request. There we go. Oh, HTTP. Oh yeah, I need to use wildcards here because it's actually Java X something HTTP servlet request. There we go. So now we have all of these parameters, and we can now jump from those parameters to the methods that receive these parameters. I'm just going to say full name. There we go. And so now we see a lot of different methods, all of which receive HTTP servlet requests. Now, some of these methods might be calling each other. So the question is, can we maybe even identify those for which we have no callers? So those are the ones that are likely triggered from the outside. And yeah, we actually can. So we can ask method filter call in, and actually I want filter not call in. So that means give me all the methods for which there are no incoming callers. And I can always ask how many are these, and we see those are 115, while if I remove this filter, we have 185. Okay, so we've already reduced this a bit. Okay, now we can go ahead and look at the names of these, list those, and again, make these distinct. And this actually shows us that the OpenRefine codebase follows standard naming conventions for naming of HTTP handlers. So they use the method names doPost and doGet, doPut and doDelete to describe handlers of post, get, put, and delete requests, HTTP requests. And there are a few exceptions to these. So we have the exceptions here, but we see mostly this naming convention holds. Right. Okay, so back to my slides. What did you just see? Well, you saw that we can identify which components the codebase interacts with, and you also saw that we are able to identify the HTTP handlers. So the places where attacker-controlled data reaches the application. All right. So with that, since we saw that the Java util zip library is used, we can go ahead and look for typical vulnerabilities associated with the handling of zips. And one of those is a vulnerability type originally described in a FRAC paper in '91, which is that in archives, the names of the entries might actually contain control characters, such as .. And if that's the case, then you need to filter for these. You need to discard that .. Otherwise, as you use the entry names to open files, you can run into a path traversal condition. Now, this has actually been a famous kind of bug this year. It seems to have been rediscovered in 2018, and so a shiny logo was put on top, and it is now called zip slip, and that's essentially what we're going to look for as well in OpenRefine now. And if you're interested more in this vulnerability class, then I recommend checking out this YouTube video on the details of this. Now, how does this kind of vulnerability surface specifically in Java code? Abstractly speaking, what happens here is that names of archive entries are used unchecked as path names when opening a file. And now, concrete in terms of APIs, well, there may be different APIs at use, but the most common pattern that you will see is that somebody calls zip entry get name, and that name that you then get of that zip entry is used in a constructor of a file. So the line that you see right at the bottom here of the document, which is file F is new file entry get name, that would be like a vanilla and very condensed example of this kind of vulnerability. Of course, it might be that entry get name is called much further up, and that it propagates through a bunch of transformations before it eventually reaches the constructor of file. But yeah, this condenses what we're looking for. And I will now show you how we would look for those zip-related bugs. All right, so still in the shell. Give me a second. Checking for. There we go. Okay. So first of all, we know that we are interested in methods that in the method getName of the class, well, somewhere in Java util.zip. There we go. We can say full name, L. There we go. And we see there's only one method. It's exactly the one that we're looking for, and it's Java util zip entry getName. So there is a reference somewhere in the code to getName. And the next thing we want to do is we want to see who is the caller of this method. Caller. So who calls this? I'm going to say full name again and L. And we see there's only one caller, and that's the method explode archive. So that's pretty nice. We know we don't need to deal with lots of different functions here, lots of different calls, but actually in this simple example, there's only one method called explode archive that calls getName, and then all we want to know now is what actually happens with that getName. So now what we will do is we will track the return value of getName, and we'll call that a source of information. There we go. So now we have a source, and we want to see whether this ever propagates to a file constructor. So file constructor, what would that look like? Method full name dot slash so file, and if you know some Java bytecode, so this is how typically the constructor is named, so init, and we'll take a look at that for a moment. So yes, there are a bunch of those. There are actually several of those, and what we need to ensure now is that we only look at parameters that are strings. There we go, string. So what are these? These are paths, usually. There might be exceptions, but usually these are paths. So what we can see here is that actually we've limited this to 3 methods. Full name, there we go. Yeah. So yeah, we did capture 2 that we actually did not want to capture, which is the org, Apache Commons, IO filter, and so on. But these are the 2 constructors that we do want to capture, which is the constructor, so the first parameter used in file init with 1 parameter, and the second one in file init with 2 parameters. All right. So let me just fix this. I will say Java IO. Yes, and then we only have these 2. Right. So these 2 parameters are going to be our sinks. There we go. And now next we can just ask, are there sinks that are reachable by the source? And can you give me the flows for those? And then the data flow engine ran a bit and it gave us back the flows. And well, the screen is not very big, but I'm just going to zoom out so you see that usually if you have a bigger screen, you get this nice table here. And you actually see exactly where the zip entry is read. And you see the entire path, the entire data flow path up to this call to init, file init. And so that means, yes, there is a path from getName to this constructor. There are actually several of those paths. But now we need to additionally ensure that nothing happens on the way that looks like a typical escaping or checking for // essentially. And so we can do this as well with Ocular. Of course, this is not going to be 100% exact, but the point the point of this is we should only give something to be reviewed to a manual for manual review if we've already made sure that it doesn't look like it's okay after all. So what we can say now is we can ask, we can ensure that the flow does not pass through anything that looks like escape or sanitize or contains or starts with, for example. So those will be the typical sequences that you use to then check whether something is whether something contains .. And if we now say, give me all the flows for this, and we still get flows, which we do. So we still get, let me just actually check, distinct. We still get 8 flows for this. So that's a very good indication that this is a vulnerability. And to make it short, we took a look at this, and yes, it is a vulnerability, and we did get a CVE for this, and it's been fixed by the developers in a newer version of this product now. All right. Yeah, maybe a bit about the impact of this vulnerability. What it means is that you can write arbitrary files. You cannot overwrite files, but you can write to arbitrary locations. And for example, if you imagine a web server where you can now write a script file in some place that can be reached via HTTP, then you can write your code there and send an HTTP request there and execute arbitrary code. So that's the impact of that. Now, one more thing that we can actually check here is we know that this call to getName is only ever made in the method named explode archive. Okay, let's first see whether this method exists. There we go. Yes, it exists. And now another question would be, can we actually trigger this explode archive from the outside? And as we found out earlier in our investigation, most of the HTTP triggers are actually called do, get, or post. So in other words, if we can show that there is a call chain from a do, get, or post to explode archive, then it looks very much like this can actually be triggered. And we see, yes, there are 2 call chains here. And we can even see what the methods are called. And one of them is called the default importing controller do post. So the way this program is architectured, there seems to be one default importer which receives post requests, and that one also receives zip files, and it will eventually pass this to explode archive. All right. So that's it for the for the zip-related vulnerability. So let's go back into the slides. Another vulnerability type that's been popular this year and is now even part of OWASP top 10 is XXE, so XML External Entity Processing. And as we already saw when we did our initial investigation of what's in the code, there are different XML libraries used here. And so the way this vulnerability works is if an attacker is able to provide an XML file, then if the XML parser is not configured properly, then they can actually reference external resources as part of the XML, and doing so, they can read files of the system and even post those files out again to the attacker. At least, so to date, they can do that via FTP still. And OWASP actually has a cheat sheet that tells you for different types of parsers what you need to do to make sure that XXE does not work. And by default, it does work if the attacker can provide the XML file in completely. And so what we need to look for here is the configuration of the parser. And for XML input factory, that's something that's used in OpenRefine, as we'll see in a moment. These two calls need to be present, which is support DTD must be set to false. And then this is supporting external entities must be set to false. I don't know if both of them or either of them, but yeah, you need to configure it in this way, otherwise you'll end up with an XXE vulnerability. So yeah, let's check for that. So this is a bit different. We're not looking for data flow. We're actually looking at the configuration of XML parsers. And so what we can do here is, let me just see. So first of all, let's check what kind of XML related types are used in the first place. So I'm just going to say dot star XML dot star, and then look at the name. There we go. Right. And so we see XML input factory here in the back. And that's what also showed up on the OWASP cheat sheet. And that's where we were told, well, if you use XML input factory, then you're going to need to configure this input factory in a certain way. Let me just see. Oh, there we go. So now we look for these calls to set property, and we'll be a bit sloppy here and just say, well, set property, oh, just a second, not party, property, there we go. Set property on anything that's called XML, that should be sufficient. And just show us all the calls to that and show us the code for that. That's it. And so there you see, there are only two calls here to set property. And one sets is replacing entity references, and the other sets is call asking. And so both of these are unrelated to restricting the use of DTDs. And so if there is actually somebody using this XML parser, then it's very likely to be an XXE vulnerability. And so that we can also check. So to use this parser, you would need to take the XML stream reader, and on that you call next, and we can check who this is called by. I'm just going to say CPG method, so those are all the different methods. Full name.l. Yeah, and that shows us, yes, there are a bunch of different methods which actually call next, so which will result in parsing of XML. And then finally, we can see if a flow exists from, let me see, from an input factory to next. Parameter index 0. Okay, so this is the just a second, the sync. No, we don't need called by. There we go. So what we have here is the instance parameter of XML stream reader next. So the object that next is called on, and we are going to make this our sync. There we go. And as a source, we define CPG method full name XML input factory create there we go, and the return value of that. Oh, I said source here, and this is the sync. Yes, correct. Okay. So, and again, same trick, sync reachable by source, flows, L distinct. We don't care what it passes through. And we see, yes, there are 4 flows here existent. And so, yes, we have an XML parser that isn't configured correctly, and it's actually being used. We could do that additional test of whether it can actually be triggered from the outside. That's the case. So I won't further bother you with that. And this as well was a reported vulnerability and has been assigned a CVE. All right. All right. So finally, what I want to show you is that while exploring code interactively with Ocular is fun and useful, but what you can then also do once you have a bunch of queries that you want to fire again and again on other projects that you audit, you can actually call Ocular in non-interactive mode and simply provide a script. And the results of that script, we allow them to be piped out in JSON format or in text, or in just text lines essentially, so that you can then process them with your with other tools that you wrote, and particularly tools that you wrote in other languages. So I'll just show you that. So I will exit this interactive shell now, and I created a small script called what is it? Scripts my script, right? And so all this does is it loads the CPG, and then it, as an example, takes all the methods and then just outputs them in pretty JSON, and this I can call as well. Let me see. Ocular, wait. I'm going to see how this is not in the history. I'm going to need to find out how it works. I think it's like this: scripts, my script, parameters, and then the first one was called CPG file name equals CPG bin zip, and then out file name equals foo.json. Okay, and now it tells me how this really works, which is this should be params. There we go, and script. Yeah, so now it executes this script, which loads the CPG, and then in the end outputs all of the methods into foo.json. Just an example. You could have also run the queries that I ran in that interactive shell. And there we go. So there's foo.json containing all of the methods, all of the information we have about methods in a JSON file for you to process with Python script or whatever you'd like to use. All right. Okay. So a quick summary, and then we can take some questions, of which there are a few, I think. So you saw a demo of Ocular today, and we ran it on OpenRefine, or formerly Google Refine. We showed you how you can create code property graphs from Java bytecode. So we also have input modules for other languages, but yeah, our The first language module we developed was Java bytecode, and this is the one that we make available in the trial version. We showed you how you can discover dependencies in your code, how you can discover HTTP triggers in your code as examples, really. You can if you're interested in other kinds of communication with the outside world, you can create similar queries that will do that for you. You essentially need to know a bit about the APIs that are used out there. And we showed you that this is actually effective in practice, and it allowed us to quickly identify two vulnerabilities in OpenRefine. One, a path traversal related to zip file processing, and the other, an XXE vulnerability in the processing of XML files. So yeah, feel free to check it out. You can download it at Go ShiftLeft.io Ocular free trial, and documentation is coming up. There are quite a few nice guides already at Ocular ShiftLeft.io. All right, and that's that. Okay, so I'm gonna see. Okay, so there's a chat and there are some questions. Let me see first what the question tab tells me. Quite a few questions. All right, so let me sort this by Jocelyn Feast asks, does Ocular come with a set of predefined rules that can be automatically checked? Like if there's a match for zip get name, check for the path traversal. So yes, the Ocular full version does. So we actually have an additional language that simplifies this even more and allows us to, for typical data flow problems, to write rules that can just be loaded. And so for the standard libraries that you'll find used all over the Java web, we have existing rules that you can just fire up and use. But this is not available in the trial. The trial just gives you the capabilities, but not the queries, which we kind of consider the, let's say, the batteries of our approach. Jocelyn Faced also says the tool looks really amazing. Thank you. And then what is this? So here's the question from Jayton Hansity. Is Ocular mainly targeted for analysis of libraries where we don't have the source code, or does it also have additional capabilities for when the source code is available? So so for Java, we process the binaries, and if the source code is available, then we can guarantee that we have the names of identifiers of variables, which we might not have if the jar has been built to strip that information. So yes, having the source code is definitely better, but the nice thing is for Java, it also works on the bytecode. Now for other languages, this is different. So for C and C++, for example, we only process source code out of the box, and we do not process the binary code at the moment. And I don't think that's something that we'll be doing in the near future. All right. Then another question. What improvements does this have over the original Yearn besides supporting more languages? Is what Josh Watson asks. Well, many actually. I think one of the most relevant ones is that if you remember using Yearn, writing these queries was theoretically possible, but in practice it was associated with a lot of pain. I mean, you saw me jump through the program right now. The completion worked well. That's the reason. That is because we actually based it on Scala, which allowed us to do compile time checking of whether the queries actually make sense. And the Yearn query language was a groovy mess, which after running for 20 minutes, would eventually tell you that this object cannot be converted to list, and it was just very painful to use. The other aspect to it is that the original Yearn query language was not really designed at all. So you might have seen in the query language just now that there are actually a bunch of conventions that we follow so that the language is easy and nice to use, as opposed to Yearn, where I more or less randomly introduced functions that you could use and called that a language. Yeah, I'd say that's the biggest advantage here. We also have support for in-memory graph databases, which you just saw here as well. So Ocular is a lot faster than Yearn in cases where you're not processing huge chunks of code. In cases where you are, you can actually attach a graph database, just as we did with Yearn, and then it's about the same speed again. All right, anything else? So Jayton Hansity asks, are there any restrictions on the versions of Java supported by Ocular? So I think, so what we did was we made sure that the newer language constructs introduced in Java 8, so the functional language constructs, they are all now supported. The bytecode didn't change much up to Java 10. So I would need to do some additional testing to be 100% sure on this, but I believe that we currently can process Java from version 6 to version 10 up. And so, no, I would say there are no restrictions at this point for the Java version. All right. And then Peter Goodman asks, how big do CPGs get for something like a browser? So what you just saw, OpenRefine, that was about 14 MB. So let me think. So for a browser, I would expect several hundred MB. That's zip though. So once you extract it into memory, I think if you have a machine with about, let's say, 16 gigabytes of RAM, then you should be fine to process this with the memory, with the in-memory graph database. I think for something like the Linux kernel, which is still much bigger given all the drivers, I'd say use a graph database backend. But for a browser, you should be able to use the in-memory backend yes, for a browser, you should be able to use the in-memory backend with 16 gigabytes of RAM. There we go. Yeah, and I think that's it actually. Did I forget anyone? 1Q. Oh, probably something will pop up now. Yes, I still have a bit of time. Just making sure I didn't miss anything. I did miss something. What is the current performance on large and complex code bases on a web browser, for example? So there are different performance, different things that we need to measure in terms of performance. One is the CPG construction. That is very fast. That's for something like a web browser, you'll get the CPG in under a minute. The part that is most that is most costly is data flow analysis. So it's a lot about what you ask. Now for data flow analysis, we did a lot of work to put some street smarts in the sense that we terminate early to not get lost in in endless paths. We use a bunch of heuristics to make sure we don't get caught up in loops. And we actually have another blog post about this, no, actually a webinar we did on all of the little things in data flow tracking that we handle to essentially make this something that will complete within about 7-8 minutes because to do a scan for typical types of vulnerabilities. Because the goal we had, or the goal we have, is to put this into CI/CD pipelines, and there, run this per commit. Now with Ocular, you can install this into your own CI/CD pipelines, but if you do actually want something for CI/CD pipelines, what also might make sense is the product we call Inspect, which essentially gives you this whole default rule set for different kinds of vulnerabilities and does scans per commit. Okay, anything else? Does Jörn figure out that a given method call and a method in a partially specialized template go to the specialized method or to the non-specialized method? Okay. So this is about virtual methods, I guess. Yeah. So we do a bit of points to analysis to find out so if you have a class hierarchy and you really want to know which of the child methods is actually called, then yes, we do some data flow tracking to find out which method is actually called. This works many times and does not always work and can't always work. But yeah, works many times, and so I think gives us quite the edge over existing tooling. Yes, okay, yeah, I think I have all the questions now. All right, and it is 54. Great, okay. One more question from Peter. Okay, I'll take one more. Will you ever integrate with a compiler like Clang to get perfect info rather than fuzzy parsed information? Yeah, great question. We will. We actually started, but it's a lot about at the moment language module development is a lot about what customers ask for, and of course the problem you kind of have is if you do base your entire C++ analysis on Clang, then if somebody doesn't use Clang, then you can't process their code. So yes, we're planning to do this. It's in the works actually, but it's going to take a bit. And then Teresa Dayok asks, when will this webinar recording be available? I believe in a few days, maybe earlier. All right. Okay, thank you so much for all of the interesting questions. Thank you for your time. I hope you enjoyed this webinar on Ocular.